Chapter 9, Rotational Motion. This lecture will help you understand gears and pulleys. Two discs touch each other, and A is driven by a motor, and disc B turns in response without slipping. The relationship between the circumference and the diameter of the wheel is given by circumference is pi times the diameter d. If two rotating wheels are touching, the linear distance a point on each wheel travels must be the same. The smaller wheel must turn faster for the two distances traveled to be equal. Therefore, the diameter of the larger wheel times its number of revolutions equals the diameter of the smaller wheel times its number of revolutions. The diameter of disc A is little d, and the number of revolutions it makes is little n. The diameter of disc B is big D, and the number of revolutions is big N. The relationship between the diameters of the two discs and their number of revolutions is big D times big N is equal to little d times little n, or the ratio of the diameters is the inverse of the ratio of the number of revolutions. If we want the smaller wheel to rotate 2 times, which is n equal 2, for each rotation of the larger wheel, big N equal 1, we get that the diameter of the larger wheel must be twice the diameter of the smaller wheel. Since little n divided by big N is 2, the large wheel must be twice the diameter of the smaller wheel. In general, the two discs on the previous slide will slip. Gears and pulleys are used to reduce slippage in transferring rotational motion. Gears and pulleys are used to increase or reduce the angular velocity of a rotating shaft or wheel. When two gears or pulleys are connected, the speed at which each turns compared to the other is inversely proportional to the diameter of that gear or pulley. The larger the diameter of the pulley or gear, the slower it turns. The smaller the diameter of a pulley or gear, the faster it will turn when connected to a larger one. When dealing with gears, we are talking about tooth gears. The gear that causes the motion is called the driver gear. The gear to which the motion is transferred is called the driven gear. In the figure, the driver gear is A and the driven gear is B. When two gears are meshed, the teeth fit together. For any given rotation of one gear, the same number of teeth on each gear must make contact with each other. Therefore, since the number of contacts on each gear must be equal, the smaller gear turns more times for each revolution of the larger gear. The driver gear turns the driven gear. For any type of gear, we use one basic formula where big T is the number of teeth on the driver gear, big N is the number of revolutions on the driver gear, little t is the number of teeth on the driven gear, and little n is the number of revolutions of the driven gear. A driver gear has 30 teeth. How many revolutions does the driven gear with 20 teeth make while the driver gear makes 1 revolution? The number of driver teeth is 30. The number of driven teeth is 20. When the driver gear makes 1 revolution, the driven gear makes 1.5 revolutions. A driven gear of 70 teeth makes 63.0 RPM. The driver gear makes 90.0 RPM. What is the number of teeth required for the driver gear? The number of teeth on the driver gear is 70. The driver gear rotates at 90 RPM, and the driven gear rotates at 63 RPM. The number of teeth on the driver gear must be 49. When two gears mesh, they turn in opposite directions as shown in the figure. If gear A turns clockwise, gear B turns counterclockwise. If gear A turns counterclockwise, gear B turns clockwise. If a third gear is inserted between the two, as in the figure, then gears A and B are rotating in the same direction. This third gear is called an idler. A gear train is a series of gears that transfer rotational motion from one gear to another. When the number of shafts on a gear train is odd, the first gear and the last gear rotate in the same direction. When the number of shafts is even, the gears rotate in opposite directions. When a complex gear train is considered, the relationship between the revolutions and number of teeth is still present. This relationship is the number of revolutions of the first driver times the product of the number of teeth in all of the driver gears equals the number of revolutions of the final driven gear times the product of all the number of teeth on all the driven gears. A is the driver gear. It rotates clockwise. The small idler gear rotates counterclockwise. The larger idler gear rotates clockwise, and since the driven gear B is attached to the same shaft, it must also rotate clockwise. Since there is an odd number of shafts, the gears A and B must rotate in the same direction. There are 4 shafts in this gear train. Gears A and B must rotate in opposite directions. Find the number of revolutions per minute of gear D if gear A rotates at 20 RPM. Gears A and C are drivers and gears B and D are driven. Big N is 20 RPM. Since gears A and C are drivers, T sub A is 30 and T sub C is 15. Gears B and D are driven so that T sub B is 45 and T sub D is 60. Solving for little n gives 3.33 RPM. Pulleys connected with a belt are used to transfer rotational motion from one shaft to another. Assuming no slippage, the linear speed of any point on the belt equals the linear speed of any point on the rim of each pulley as the belt travels around each pulley. The larger the pulley, the larger is the circumference, where C is pi times d. The larger the circumference of the pulley, the longer a point on the belt stays in contact with the pulley. The smaller the circumference of the pulley, the shorter a point on the belt stays in contact with the pulley, which causes the smaller pulley to rotate faster than the larger pulley. When two pulleys are connected with an open-type belt, the pulleys turn in the same direction, as seen on the left. When two pulleys are connected with a cross-type belt, the pulleys turn in opposite directions, as seen on the right. The formula for pulleys connected with a belt is big D times big N equals little d times little n, where big D is the diameter of the driver pulley, big N is the number of revolutions per minute of the driver pulley, little d is the diameter of the driven pulley, and little n is the number of revolutions per minute of the driven pulley. The following are a set of problems for you to work on. Pause the video to give yourself time to work on the problems. A circular disc 30 centimeters in diameter is rotating at 275 RPM and then uniformly stops within 8.00 seconds. Find its angular acceleration, find the initial linear speed of a point on its rim. How many revolutions does the disc make before it stops? Pause the video to work on the problem. Did you get minus 3.60 radians per second squared for part A, 432 centimeters per second for part B, and 18.3 revolutions for part C? A cycle of mass 510 kilograms rounds a curve of radius 40 meters at 95 kilometers per hour. What is the centripetal force on the cycle? Pause the video to work on the problem. First, convert 95 kilometers per hour to meters per second and get 26.4 meters per second. The centripetal force is 8,900 newtons. What power is developed when a tangential force of 175 newtons is applied to a flywheel of diameter 86 centimeters, causing it to have an angular velocity of 36 revolutions per 6.0 seconds? Pause the video to work on the problem. The power is the torque times the angular velocity. First, find the angular velocity in radians per second and get 37.7 radians per second. The torque is the applied force, 175 newtons, times the moment arm of 0.43 meters. The total power is 2,800 watts. The larger of two gears in a clock has 36 teeth and turns at a rate of 0.50 RPM. How many teeth does the smaller gear have if it rotates at 1/30th of a revolution per second? Pause the video to work on the problem. The rotation rate is 2 RPM. The number of teeth on the driven gear must be 9. Your assignments are to read Chapter 9 in the textbook, and your homework assignments are due March 16th. Watch videos on Blackboard for this chapter.